So, hello to the YouTube audience, basically everyone who's watching on YouTube. So, since no one has joined the session in person yet, so I'll be waiting for like 5-6 minutes before starting to discuss the problems or beginning the session so that a few people can join. So, I'll be starting in 5 minutes. Okay, so Hi Rasika. So I guess no one else is joining, or maybe like even if someone else can joins, they can join the session midway. So I guess we can get started by then. So just to reintroduce myself for so Rasika joins the session regularly, but otherwise just to reintroduce myself for the YouTube audience. So hello everyone, I'm Lakshya Saggi, the problem solving TA for the NPTEL Competitive Programming course for the Tuesday 6 to 8 p.m. sessions. So this will be our seventh session, I believe. And in this session, we'll be discussing the problems related to this week's content, which were mostly about minimum spanning trees. So Prim's algorithm, Kruskal's algorithm, and so on. So once again, I'll be assuming that you guys, so while discussing the problems, I'll be assuming that you guys have gone through the lecture videos first and we'll strictly be trying to solve only the problems based on the contents of the lecture videos. So yeah, so keeping this in mind, I guess we can get started. So just let me share my screen. Okay. So I hope my screen is clearly visible. So if it is not, if there are any issues with my audio or my screen, you can let me know via chat, Rasika. Otherwise, I'll just assume that it's visible. So yeah, with this, I guess we can get started. So in today's session, just to give a brief summary, so we have something like 8 problems. So not a lot of problems for today because like last week, I'm feeling a bit down today also. So this will also not be a very long session. We'll try to solve all the problems, obviously, but I don't think today's session will take a lot of time. But yeah, I guess we can nevertheless get started. So the first problem is consider the graph G given below. So we are given this graph G, which has the vertices A, B, C, D, and E. And now we have to find the cost of the minimum cost spanning tree for the given graph. So once again, I'll be assuming you guys already know what a minimum cost spanning tree is. So we are just given this graph and we have to find the cost of the minimum cost spanning tree. So again, from the lecture videos, we know that there are several algorithms to find minimum cost spanning trees. One of them is Prim's algorithm, the other one is Kruskal's algorithm. So we can use any of those, and by those we can find the minimum cost spanning tree for this graph. So note that once again that there can be multiple minimum cost spanning trees in a graph, but the cost of all the minimum spanning trees will be the same. So just keep in mind what I have said. So I'll just write this as a note first of all. So starting note, there can be multiple minimum cost spanning trees for a graph, for a given graph, but the cost of all those spanning trees will be the same. So cost of all those minimum spanning trees will be the same. So this is something which I believe should be clear to everyone. Why is this the case? That so like we can consider this problem now. So just saying this that there can be multiple minimum cost spanning trees for a given graph, but cost of all those will be the same. So we don't have to. So in this problem, we don't have to output all possible minimum spanning trees. We just have to output the cost. So like Prim's algorithm can give one minimum spanning tree, Kruskal's can give another. Maybe in this graph, I think it will be unique, but in some other graph, Prim's algorithm may give one spanning tree, Kruskal's may give another. But the key thing is that the cost will always be the same, which Prim's and Kruskal's give us. So yeah. So I'm not writing this down. I'm just discussing this. That this note is important. So now the problem statement says that we have to find the cost. So just finding the cost, we can use any of the algorithms, Prim's or Kruskal's, doesn't matter. So let's say we start with Prim's algorithm, and let's say we start with the vertex A. So let's use. So our focus for this week for this session will be on Prim's and Kruskal's algorithm, mainly because these algorithms are very important in algorithms literature, and most of your this week's assignments problems are also based on these two algorithms only. So yeah, let's use Prim's algorithm starting from vertex A. Starting from vertex A is this to find MSG. MSG is nothing but minimum spanning tree. So yeah. So if we start from vertex A, so which will be the first vertex which will be added? So there are which will the first edge which will be added in the spanning tree. So from A there are only two outgoing edges. So I'll be assuming that you guys already know what Prim's algorithm is. So we start from a vertex and then we just see the outgoing set of edges from that vertex, and like basically we initialize a set of vertices and then we see the set of outgoing edges from those set of vertices and select the minimum cost edge, and that's how we keep expanding our set of vertices. So initially the set contains only the vertex A, and now the set of outgoing edges from A are only these two edges, the AB edge and AC edge. So among AB and AC, AB has a cost of 1 and AC has a cost of 2. So AB has lower cost, so we'll add the edge AB to the uh, edge AB gets added to MST. So in step 1, edge AB gets added. And after this, in second step, so maybe I can write it like this. Then the edges get added in the following manner. And what's the manner? The manner is something like this. So yeah, HAB gets added to MSG after this. So now this set AB is our set of vertices now. So out of this set AB, the set of outgoing edges are the edges AC, the edge BC is the edge BC, the edge BE, and the edge BD. So I'm assuming that you are able to follow. If you're not able to follow, just you can type in chat and I'll try to explain it a bit more clearly. So right now what I'm trying to say is now our set of vertices contains the vertices A and B. So now the set of outgoing edges are this edge of cost 2, this edge BC of cost 3, this edge BE of cost 5, and the edge BD of cost 4. So out of these, the minimum cost edge is the edge AC of cost 2. So AC gets added to MSG. So as soon as, so maybe I should keep track of the set of vertices also, which are covered. So let's say I call that set S. Initially, that set contains only the vertex A. After adding the edge A comma B, S now becomes equals to A comma B. After this, as soon as we add the edge A comma C, the S gets updated to A comma B comma C. Right. So now A, B, C, all these three vertices are added to our MSG for now. And now the set of outgoing edges from this ABC. So note that this BC edge is not outgoing from this set, as both of the endpoints are inside the set S only. So yeah. So out of this set ABC, the edges going outwards are the edge BD, which has a cost of 4, the edge BE, which has a cost of 5, and the edge CE, which again has a cost of 4. So now we sort of have two choices for our edges. Either we can add the edge BD or we can add the edge CE, because both of these are minimum cost edges, right? This 5 is greater than 4, but two edges have cost 4. And in Prim's algorithm, if we encounter two edges of the same cost, it does not matter which edge do we add. So we can add any of these two edges, either BD or the HCE. So let's say I add the HCE. So HCE gets added to MSG. And what this does is this updates are set to A, comma B, comma C, comma E. So after this, now A, B, C, E are added to our. So these four vertices are being added to have already been added to the MSG. So now only one vertex remains, which is the vertex D. And we can see from this outgoing set there is only one edge. From this set of vertices, there is only one edge which is outgoing, which is the edge BD, and it again has a cost of 4. So the edge BD gets added now to MSG. And now we have spanned all the vertices. All the vertices are now covered. So now the S set has becomes A, B, C, E, and the vertex G. So the MSG contains so one possible MST for graph G contains. So why I'm writing this one possible? Maybe there is only one MST in this graph, but I'm just writing for the sake that there is one possible. Like there may be multiple or there may not be multiple, but at least there is one MST. And we just might need to find the cost. So cost of all the MSTs will anyways be the same. So we are just interested in getting any one MST, and we have obtained this. So then this contains the edges AB, the edge AC, the edge CE, and the edge BD. So these are the four edges which are contained. So cost of this MST is, so cost of the MST is nothing but cost of edge AB, which was 1, and then the edge AC, which had a cost of 2, and then the edge CE, which had a cost of 4, and again the edge BD, which had a cost of 4. So 1 plus 2 plus 4 plus 4, which will come out to be 11. So 11 is the correct answer here. I'll just underline this also. Maybe I should underline this whole line. Right. So yeah, so this is the answer. 11 is the correct answer for this. So yeah, so I hope it is clear to you, everyone. Again, if something is unclear, you can just reminding you that you can type in chat and let me know. So yeah. Then I guess we can move on to the second question. So in the second question now, we are given a complete undirected graph. So what is a complete graph? So complete graph is a graph which has edge between every possible pair of vertices. So since there are n vertices, the graph has something like n choose 2 edges. So which is n times n minus 1 by 2. And let's say the vertex set is denoted by the number 0 to 4. So there is a vertex labeled 0, there's a vertex labeled 1, there's a vertex labeled 2, 3, and so on, 4. And now we are given the adjacency matrix for this graph. And what's an adjacency? Or maybe not an adjacency matrix, but a weight matrix. So what this matrix says is that every entry Wij in the matrix W, so this is the matrix given to us, the matrix W, the entry Wij denotes the weight of the edge from vertex I to vertex J. So from let's say vertex 0 to vertex 2, so the weight of the edge from vertex 0 to vertex 2 will be nothing but, so we need to select the 0th row. So so the indexing of the rows and columns starts from 0, not from 1. Just keep this in mind. So 0th row and second column will give us the edge weight between the vertices 0 and 2. So 0th row is nothing but this, and second column is, this is 0th column, this is first column, this is second column. So the edge will be, so the edge between 0 and 2, vertex 0 and 2 will have a weight of 8. Also note that we could have also similarly found, like, since this is an undirected graph, so finding the edge from 0 to 2 and the edge from 2 to 0 will be the same actually. So that's why, like, finding 0th row's second column and second row's 0th column should give us the same answer. should give us the same value. And you can see it is indeed the case that second row of 0th column will again have a weight of 8 only. So generally for an undirected graph, this sort of weight matrix W will be a symmetric matrix. That Wi comma j entry will be equal to Wj comma ith entry. Because in an undirected graph, the edge from I to j and j to I are actually the same. So I hope this is clear. So now the problem statement says that we are given the graph G in this form, in this matrix form, and now we have to find the minimum possible weight of spanning tree. So again, what we should do here is so we know this Prim's algorithm, Kruskal's algorithm for the graphs, and now instead of the graph, we are given this graph in the form of a adjacency matrix. So first thing we should do is maybe make a graph, maybe not an adjacency, but yeah. So maybe make a graph out of this W matrix. So if we can make a graph out of this W matrix, then we can obtain a spanning tree, the minimum weight spanning tree for this graph. So again, there can be multiple spanning trees, maybe multiple minimum cost spanning trees, but the cost for each of those will be the same. So we can apply any of the Prim's or Kruskal's algorithm to find it. So let's just construct the graph for this spanning tree. Let's just construct the graph for this matrix W. So there are the vertices 0, 1, 2, 3, and 4. So maybe we can create those vertices. The vertice is 0. Uh, yeah, I should write. Yeah, I think it's okay. So this is the, let's say the vertex 4. This is the vertex 3. Um, the vertex 2. And this is the vertex 1. So yeah. So these are the vertices which are given to us. So maybe I can put these here in this order: 0, 1, 2, 3, and 4. And now we are given that the edge weight from, so the edge weight between 0 to 0 is 0. There are no self loops. And now from vertex 0, so the edge between 0 to 1 has a weight of 6 because 0th row and first column entry is 6. So we connect 0 and 1 by a edge of cost 6. So this has a cost of 6. Maybe I should this also in. So yeah. So this has a cost of 6. And now we need to find. And now the edge between 0 and 2 has a cost of 8. So 0 to 2 has a cost of 8 now. Maybe I should keep it as it is just for consistency. So this has a cost of 8, and now 0 to 3 has a cost of 3. So 0th row and third column is 3. So 0 to 3 has a cost of 3 now. 0 to 3 has a cost of 3, and now 0 to 4 has a cost of 4 because 1, 2, 3, 4, fourth column is 4. So 0 to 4 has a cost of 4. So yeah. And now we come to the first vertex neighbors. So first row and first entry is again 0. 0th entry we already know is 6. So now first row and second column, so vertices 1 and 2 have an edge of length 12 between them. So so the edge weight between 1 and 2 is nothing but a weight of 12. So something like this. And now between 1 and 3, we have a weight of 4 because first row and third column is a weight of 4. So 1 and 3 have a weight of 4. Now 1 and 4 have a weight of 2 here. here to everyone. And similarly for third vertex, we'll have uh, the vertex number 2. The vertex number 2 and vertex number 1 have a weight of 1 between them. So, so 0, 1, 2. So sorry, the vertex number 2 and vertex number 3 have a weight of 1 between them. So 2 and 3 have a weight of 1. So these two have a weight of 1. And now 2 and 4 have a weight of 3. So 2 and 4 have a weight of 3. So this might seem cumbersome, whatever I'm doing, but uh, problems like this can pop up where you're actually given initially the W matrix and then you have to create a graph out of it. So even though it is arduous, it is something that we should practice doing. So yeah. And now for the vertex number 3, we just need to find its edge to the vertex number 4, which has a weight of 2. So 3 to 4 has a weight of 2. So 3 to 4 has a weight of 2. Okay. So now we have this graph with us now. And this graph contains all the edges have some weights. And now for this graph, we have to find one possible minimum spanning tree. And for that minimum spanning, like we have to find out the cost of that spanning tree. So note that in the previous problem, we used Prim's algorithm. Now let's say we use the Kruskal's algorithm. So, so I'll copy paste this picture into, so we'll keep this diagram in mind. After while uploading this document, I'll post the picture in this document itself. But for now, let's keep these in different tabs. So for this, let's use Kruskal's algorithm. Kruskal's algorithm to find MSG. To find MSG. Right. So how do we find? So the edges get, so in Kruskal's algorithm, let's again initialize something like this. The edges get added in the following manner. And what's the manner in which the edges get added? So maybe I'll just, okay. Okay, maybe we can. So let's see the diagram first. So in Kruskal's algorithm, what we do is we select the minimum weight edge first and add it to our spanning tree. So here one edge has weight 6, 4, 2, 2, 8, 4, 2, 2, 12. So this one is the minimum possible weight. So the edge 2, 3 gets added to the spanning tree. So edge 2, 3 gets added to the MSG. So initially this edge 2, 3 gets added. And now what we do is maybe yeah. So after this, so now this 2 and 3 get connected. After this, we'll have to consider this 2 and 3 as a super node. So the 2 and 3 are now acting as a super node, or maybe not exactly a super node, but something like that. The edges. So the edges between the connected components should not be added again, or something like that. So 2 and 3 now get connected. So we won't add any other edge of between two, which lie between 2 and 3. So it will become a bit more clear when we proceed with the algorithm. So for now, we have added the 2, 3 to the spanning tree. And now after this, we'll look again into the next smallest edge. So this had weight of 1. And after this, and these two edges have a weight of 2. So we can add any of these edges to our MSG as we want. So let's say we add the edge 1, 4 first. So let's say we add this edge 1, 4 to our MSG. So what happens is edge 1, 4 gets added to MSG. So now this 1, 4 forms one connected component This 2 comma 3 forms one connected component, and this 0 is a connected component in itself. And now we'll only add those edges which connect two different components. If you remember in Kruskal's algorithm, we do something like this. So now again, after this edge, after this 1 comma 4 edge, the other smallest edge, the next smallest edge is again of weight 2, which is this edge of between 3 and 4. And note that this edge between 3 and 4 for that, right? So this edge between 3 and 4 also connects actually different component. So it connects the component of 1 comma 4 to the component of 2 and 3. So this edge again gets added to the MSG. So the edge 3 comma 4 gets added to the MSG. Gets added to the MSG. And after this, so this 1, 2, 3, 4 forms a single component now. So as 1, 2, 3, 4 has formed a single component now, so we can ignore all the edges uh, which lie between 1, 2, 3, 4. So something like we can ignore all the edges of the form 1, 3, 1, 4, 3, 4, 2, 3, and so on. So all of this forms a single component, and the 0 is the other component. So we only have to look at the edges which go from 0 to any of the vertex of this component of 1, 2, 3, 4. So the only edges are the 0, 1 edge, which has a weight of 6, the 0, 2 edge, which has a weight of 8, this 0, 3 edge, which has a weight of 3, and this 0, 4 edge, which has a weight of 4. So out of these, this 0, comma 3 edge of weight of 3 is the minimum because the weights are 6, 8, 3, and 4. So yeah. So that's why this is the minimum weight edge. And the 0, 3 edge will get added to the MSG. Edge 0, 3 gets added to the MSG. So what does our final possible MSG consist of? Maybe I should just write it down. So one possible MSG for this given graph G contains the edges 2, 3. The edge is the edge 1, 4. The edge 3, 4. So note that there might have been other possible MSGs also, but we are looking at this one because we need to output the cost only, and cost is always unique. So this. So these 4 edges are the ones which are contained in the MSG. And now let's see. So the cost of the MSG will be nothing but sum of the cost of these individual edges. So the H2 comma 3. So we can look at the cost from this matrix also, but we can directly look it from the graph also. So this 2 comma 3 had a weight of 1. Then we had this 1 comma 4 with a weight of 2. This 4 comma 3 with a weight of 2. So the first 3 terms will be something like 1 plus 2 plus 2. 1 plus 2 plus 2. And then the 0 comma 3 edge had a weight of, okay, the 0 comma 3 weight had a weight of 3. So 1 plus 2 plus 2 plus 3. And this will be equal to 3, 5, and 7, and 8. So yeah. So this will be the answer. So 8 is the cost of the minimum spanning tree. So some people like to write it as weight of MSG. Some people say cost of MSG. So both are the same thing. So weight and cost is same thing. So yeah. So now I guess we can move on to the third question then. So third question is again a problem based on Kruskal's algorithm. So it says find out the. So these sorts of problems are so also present in your assignment. So that's why I'm doing these sorts of problems. So yeah. So the problem says that consider the given graph which contains these vertices A, B, C, D, E, and F. And now which of the following can be the sequence of edges added in that order to create a MSG using Kruskal's algorithm? So we are given some options and we have to find out which of these sequences corresponds to adding edges using Kruskal's algorithm. So Kruskal's algorithm was a similar algorithm which we used to in the second problem. So in Kruskal's algorithm, as we had already said, so we first find out the minimum weight edge. And out of these edges, the minimum weight edge is the edge AE, which has a weight of 1. So maybe I should write down again. I should just copy this. So I'm just copying. With that in the following manner. Okay. So okay. Now it works. So initially, we add the minimum weight edge, which is the edge AE. So edge AE gets added initially. So edge AE gets added to the MSG. And after adding AE, this AE becomes a single connected component now. So now we look at the edges which are between components again. So now the minimum weight edges are these possible edges, the edge EC, which has a weight of 2, the edge CD, which has a weight of 2, and the edge AD, which has a weight of 2. So any of these can be added, either AC or CD or AD. So let's see the options. So we are already given some options. So let's try to minimize our options, or let's try to rule out some options. So the only three possible edges which can be added right now are EC. So initially AE is added, which is added in the all of the options. So after this, we can add EC, CD, or AD. Any of these should work. So one option gives AD, one gives CE, and the other gives CD. So all of these actually are possible till second iteration. So till second iteration, all of the options are correct. So okay, so maybe we should go option by option, or okay, maybe we should not do it like this. Maybe there are multiple possible options in this problem. Like, so there may be multiple possible sequences which are correct. So this can also be correct, this can also be correct, this can also be correct, or something like this. So maybe we should uh, do it by option, like which of these options are possible. So let's see option A first. So in option A, the AE edge gets added initially. So which is correct because AE was the minimum weight edge. So now A and E become a single component. Now the edge AD gets added, and now the as soon and this AD is again correct because after adding AE, we have three edges of weight 2 and we can add any of the edges. So the edge AD gets added, and now the component ADE becomes a single component. The ADE becomes a single component. And as soon as this happens, again, we have these two edges still as intercomponent. So now one of the edges of CE or CD should be added because these are the edges which have minimum weight and are between components. So now in option this, A, they add the edge CD, which again is correct. So we had two choices. We could have done CE or CD. It's our choice. So let's say we add the edge CD. So what this results in a component. So initially earlier ADE was a component. C also gets added to the component. So this ADEC becomes a single component right now. So these four vertices form a single component. And now we have to look at only the edges which are between components. So with the edges which are between components are the edges CB, which has a weight of 3, the edge AB, which has a weight of 4, the edge AF again with a weight of 4, and the edge EF with a weight of 7. So out of these, the minimum cost is for this edge BC, which is 3. So now the edge BC should be added, which is again correct. So after adding the edge BC, the whole component becomes, so one component becomes this A, B, C, D, and E, and F is in another component. So now again, the two inter-component edges which are remaining are these FE edge of weight 7 and the AF edge of weight 4. So out of these two edges, this AF is the edge with lower cost. It has a cost of 4. So AF should be added, which is again correct. So option A is actually a valid sequence. So valid sequence. So we'll have to do this option by option. So because uh, since like in step 2 there were multiple possible choices, we could have added either of these three edges of weight 2, and what edge we choose results in a different MSG or something like that. So that's why we have to check option by option if all possible options give the same give correct sequences or not. So let's see option B now. So in option B again, AE gets added initially, which is correct, and then they add the HCE. So right till now, AEC form a single component, and these F, D, and B form individual components. So now this component AEC. So now the intercomponent edges which are smallest weight are these edges of weight 2, the edge CD and the edge AD. So one of the edge AD or CD should be added in Kruskal algorithm. And as we see in this option, they add the edge AD. So till now they are correct. And the component forms till now is this component A, C, D, and E. So again, we have formed this component till now, the component A, C, D, and E. B is a single component, F is a single component. And now note that okay, yeah, okay. So now note that the intercomponent edges are this edge BC, the edge AB, the edge AF, and the edge FE. And this has weight of 7, 4, 4, 3. So the minimum weight is of this component of this edge BC. So this edge BC should get added, and which is correct. And similar to last option, in the end we will have AF edge as added. So option B is also actually a valid sequence. So let's come to option C then. So in option C, they initially add the edge AE, which is again correct, which was the minimum cost edge. And now they add the edge AD, which is again correct because we had a choice of these three two weight edges. So till now the component formed is this ADE component. And now we should actually be adding the either of these two edges, either of these weight two edges. So either we should add EC or we should add CD. But what they add is the edge BC, which has a weight of 3. But we still had two intercomponent edges of weight 2 available to had these two edges available to us. So actually this is incorrect. So we can't add the edge BC right now. We should have added one of the edges CE or CD. So this is invalid sequence. So invalid as either of CE or CD should be added before PC. So yeah, I hope this is clear to everyone. If it is not, you can ask me by chat. Okay. And now let's come to option D then. So option D sequence is again the edge AE initially, and then the edge CD, which is again correct. It's as it's a weight 2 edge. And note that right now the components after adding the C will be this AE will form one component, this CD will form another component. So these two will be disjoint components. So now the inter-component edges of minimum weight will be this edge CE of weight 2 and the edge AD of weight 2. So adding any of these edges makes sense. So we can add the edge AD. So till now we are correct, and the component formed is this AEDC component, as these two components get merged after adding the edge AD. So this AEDC is a component which is formed right now, and after forming this component, the minimum cost edge, again like in previous options, will be this edge B comma C, as it has a weight of 3. The other edges have a weight of 4, 4, and 7. So we should add the edge B comma C after this. But here in this option, they add the edge A comma B, which is sort of incorrect as it has a weight of 4, which is wrong. So option D is invalid, as B comma C should be added instead of A comma B. Yeah, I should try. Yeah. So now let's come to option E. And option E again, we see that in option E, actually option D and option E are similar till this stage, till we don't add option the edge A, B, or B, C. So till this A, E, C, D, and A, D, both of these options are same. And while adding these three edges, we already saw that the algorithm was correct. And till region of this edge, the component form will be something like A, D, C, E. This component, this will be a single component, and F and B will be individual components. And now, as we said that we should add the edge BC right now. And note that they are adding the edge BC. So after adding the edge BC, this whole becomes a single component, and F isolates as another component. And now the minimum weight intercomponent edges will be this edge of weight 4, as there are two edges, one of weight 4 and weight 7. So 4 is lesser. So we'll add the edge AF, and this is what they are doing. So option E is actually valid. So the valid sequences are options A, B, E, and C and D are invalid. So hence options A, B, E are correct. So note that these options, the option A and option E has different edges. Like, okay, maybe they are the same edges, or okay, let's see this option A and option B, even though both are valid using Kruskal's, but note that both of these options have different set of edges. Like edge CE is not present in option A, and the edge CD is not present in option B. But are actually, both of these options are actually forming an MSG, as they are giving us, as they are formed using Kruskal's algorithm. So this is an example where there can be multiple possible MSGs for a given graph. So this graph has at least two MSTs, which are option A and option B. And you can easily verify yourself that cost of these two spanning trees will also come out to be the same. So yeah, just a food for thought, and I'll just maybe underline this correct answer. Okay. So now let's come to the fourth question. Maybe I should do it next page. So yeah. So fourth question, I believe, is another question which is similar to Prim's and Kruskal's. So now it asks us which of the following is the correct sequence of edges added using Prim's algorithm. So earlier we used here Kruskal's algorithm, going option by option. Now we have to find out the valid sequence, assuming that we are adding edges using Prim's algorithm. And A is considered as a source vertex. So this vertex A is the source vertex right now. So maybe we can do option by option here also. So again, an arduous task, but somewhat similar to the questions given in the assignment. So yeah, so we'll be looking into this. So let's come to option A first. So option A says, so note that we are doing Prim's algorithm and we are starting with the vertex A. So as soon as we start with the vertex A, uh, what we initially have to do is we have to select the minimum outgoing edge of this out of this component. So from this A, the outgoing edges are this edge of weight 2, 3, this edge of weight 2, this edge of weight 1, and this edge of weight 6. So this edge AD is the minimum weight edge as it has a weight of 1. So AD should initially get added. And this is what they are doing initially. So till this step, it is correct. And after adding the edge AD, now this AD becomes a single component, and we have to find out the lowest weight edge coming out of this component AD. And note that the edges coming out of this AD component are the edges AB of weight 6, DE of weight 4, this DC of weight 3, AC of weight 2, and AS of weight 3. So the minimum weight edge actually is this edge, AC of weight 2. So this should get added in the Prim's algorithm. And this is what is getting added in option A. So till the edge AC, the option is correct. So right now the component which we have obtained is this a component CAD. So the CAD is the component which we have obtained till now. And now we see the set of outgoing edges out of this component. And out of this component CAD, the outgoing edges, one has a weight of 6, one has a weight of 4. This edge SC has a weight of 2, and this SA has a weight of 3. So again, this SC edge has a weight of 2, and it's the since 2 is the minimum, so this should be added. So this C comma S edge should get added if we are doing Prim's algorithm. But note that they are adding the edge A comma S in this option. So that's why this option is actually incorrect. The sequence is invalid as C comma S should be added instead of A comma S. So note that I'm just spotting out the first mistake. Maybe there can be mistakes later on in the sequence also. But the first step at which we get a mistake is this, that C comma S should have been added before A comma S instead of A, because A comma S had a weight of 3 and C comma S had a weight of 2. So yeah. So option A is invalid. Maybe we can go to option B then. So in option B, again, we add the edge A comma D initially, and then we should be adding the edge A comma C as was observed in option A, but we are adding the edge B comma E. So note that even though B comma E edge has a weight of 1, but it's not connected to our component which we are making. So note that we are using Prim's algorithm and not Kruskal's. If we use Kruskal's, then B comma E would have been valid, but in Prim's algorithm, we grow our component, we just grow our existing component, which is the component AD. So the edges should have one endpoint in AD at this point, but the edge BE lies outside of this AD entirely. So that's why this is also incorrect. So invalid. And why is this invalid? At this point, the edge A comma C should have been added. So even though AC has a higher weight than the edge BE, but note that since we are using Prim's algorithm and we are growing this component part by part, so that's why AC should have been added before instead of PE. Should be added instead of P comma E. So this is incorrect. So similarly, option C will also be incorrect. Because option C also has BE edge added. So maybe I can just copy and paste the reason. So by elimination method, maybe option D is the only correct, but we should still verify whether option D is valid or not. So in option D, first we add the edge AD, so the component becomes this, and then as we discussed, we should add the edge AC. So the component becomes this A, C, and D. And then we discussed that the minimum weight edge is this edge SC. So this should be added, and this is what they are doing. So till now they are doing it correctly, and the component made is this ASCD component. And out of this component, the set of outgoing edges is this AB edge of weight 6, the DE edge of weight 4, and the DF edge of weight 6. So this DE is the minimum weight edge as 4 is less than 6. So we'll be adding the edge DE now. And this is what they're doing in this option. So the DE edge gets added, and now the component actually becomes something like this. The ASCDE component. And from this component, we can actually see the set of outgoing edges is this edge SF of weight 6, this edge EF of weight 2, this edge EB of weight 1, and the edge AB of weight 6. So since since 1 is the lowest out of all these weights, so EB should be added now. And this is what they're doing. So EB and BE are the same. They're adding the edge BE now. And after this whole becomes a single component, and F is the remaining component. And between these components, there are only two edges, one of weight 6 and one of weight 2. So naturally, we'll add the weight 2 edge, which is the edge E comma F. And this is what they are adding. So that's why this sequence is correct. Valid. So hence option D is the correct answer. So I hope everyone understands this. If you don't, please type in chat so we can try to. I'll try to explain it again. Okay. Then we move on to fifth question. Fifth is a bit trickier question, so I would like you to try it yourself also at first. So we are given that G be a complete undirected connected graph on 4 vertices having 6 edges with weights 2, 4, 5, 6, 8, and 10. So note that we are given the weights of the edges. There are 6 edges and we are given the weights of the edges, but we are not given which edge has what weight. So what I'm trying to say is, okay, maybe I should be. So okay, maybe I should just copy this. Yeah. So moving this 4 here, this is the vertex 3, let's say. This is the vertex 2. 1. So yeah. So we are given these 4 vertices 1, 2, 3, 4. So we are given a complete undirected connected vertices having 6 edges with weights 2, 4, 5, 6, 8, and 10. So we are given these 4 vertices and they have 6 edges between them. So something like this. So this is the second edge. So every pair of vertices has an edge between them. That's what we call a complete graph. So I'm just drawing edges between every pair of vertices. So note that we should obtain 6 edges because 4 choose 2 is 6. So 1, 2, 3, 4, 5, 6. So we are given these 6 edges. And we are given the weights as 2, 4, 5, 6, 8, and 10. But we don't know which edge has what weight. Like the edge 1, 2 can have a weight of 2. This edge 1, 3 can also have a weight of 2. Like one of these edges has a weight of 2. The other has a weight of 4. So something like this. But we don't know what edge has what weight. So this is the main part of the problem, that we don't know what edge has what weight. And now problem asks us the maximum possible weight that a minimum weight spanning tree of G can have. So there may be multiple possible assignments of these weights to edges, right? Maybe in some cases the edge 1, comma 2 has a weight of 2. Sometime in another assignment 1, comma 3 has a weight of 2. So out of all these possible weight assignments, suppose for all possible weight assignments, we find the weight of the minimum spanning trees. So the problem asks us actually to find out the maximum possible weight which can be obtained if we use this sort of procedure. So, Rasika, is the problem clear to you? That there are a lot of weight assignments given, like there can be multiple possible weight assignments to the edges, and now we want to find out the maximum possible weight of a minimum spanning tree. Okay. So this is a bit tricky problem. Like this is not like the standard Prim's or Kruskal's algorithm or something like that. So I would like, okay, so the problem is clear to you. Nice. So I would like you to give it a try by yourself first. So let's check, like maybe you can take 5 minutes or something and you can just try it yourself. Or you can just type out any idea which you have in mind, like any guesses on how should we do this or something like that. So note that there is no correct procedure for this problem. Like there's no official procedure. It will mostly be just using some smart techniques or to find out. So yeah. So maybe if you want, you can try it for like 2-3 minutes, or like let's say 5 minutes, because this is, I believe, the most interesting problem for today's session. And and this is a bit new problem. So yeah, it might help you gain some insight on MSGs. So how should we assign these weights to the edges? So the maximum possible weight. So the MST should have the maximum possible weight. So maybe I can mute myself for 3-4 minutes till you tried yourself. Yeah. If anything comes to your mind, you can type in chat, or yeah. Okay, so the Radhika has written in chat that we should be considering sum of only 3 edges to get the total weight of MSGs. So correct, since there are 4 vertices, any spanning tree will contain only 3 edges. And now Radhika is saying that consider the larger weight 6, 8, and 10. So Rasika is saying that 6, 8, and 10 will be 3 edges, and they will have a weight of 24. And this is because like MSG will only have 3 edges. So Rasika is saying that since MSG has 3 edges, so just select the largest 3 possible weights, and this will give us the maximum possible weight of a minimum spanning tree. So Rasika, your first idea is correct that MSG will only have 3 edges, so we just need to select 3 edges out of this. But note that those 3 edges should also form the minimum spanning tree. So, like, So suppose there was a graph in which you form a spanning tree using the edges 6, 8, and 10. But that may not be the minimum spanning tree for that graph. So it's a good attempt, Rasika, but like let's say suppose for example in this problem, in this only, maybe I can make a copy of this. Okay, so uh, so let's say Rasika something like what you said right now that okay, that let's make this 6, let's make this 8, and let's make this 10. Right? So now you're saying that these three edges will give us a spanning tree of weight 10 plus 8, 24. But note that let's say even if we take these three edges of weight 10, 8, and 6, we have to assign these other weights to the edges also, right? 2, 4, and 5 will be assigned to the remaining three edges. So let's say this edge gets a weight of 2. This edge gets assigned a weight of 2. One second. Now it's a bit clearer. So this edge gets assigned a weight of 2. Uh, this edge, let's say, gets assigned a weight of 4. This edge gets assigned a weight of 5. So we need to find out the assignment also, right? So now what actually happens in this case is that this 10, 8, and 6 will not actually be the minimum spanning tree. Here the minimum spanning tree will consist of this this 2 edge and this 4 edge and then this 6 edge or something like this. So that's why the minimum spanning tree will not be of weight 24, and in this example it will be of something like a weight of 12. So that's why this idea may not actually work because like the largest weight spanning tree will definitely be this spanning tree 10, 8 plus 6, but the largest weight minimum spanning tree will not be this spanning tree because this is an alternate spanning tree for this example. So we need to be a bit more clever about this. And Rasika is so now Rasika is saying that the answer should be 11, that 2 plus 4 plus 5. And I think you obtain this by just taking the three minimum edges. But note that Rasika, this the 2 plus 4 plus 5, 11 is also incorrect as we have just seen in this example. Like in this example, the weight of MST is something like 2 plus 4 plus 6, which is 12. Because initially this 2 will be added, then this 4, then this 6. I hope it's clear to you that 11 is also not correct. So 24 is also not correct. Taking the top three is incorrect. Taking the bottom three is incorrect. So we need to do something a bit more clever than this. So, should I give you another hint, or maybe I should just uh, start explaining about it, I guess. So note that how can we go about it is, so one thing to note is we can just arrange these edges in their increasing order of weights, right? Let's say we are finding out, we are given these edge weights, and now let's say we are using Kruskal's algorithm to find out the MSG. We don't know which edge corresponds to what weight, but Kruskal's algorithm, anyways, we first sort the edges according to their weights, and after that we start seeing whether edges belong to different components or same. So let's say these are the edges, and we have sorted them in their increasing order of weights. So first of all, note that the first weight of 2 can be assigned to any edge without loss of generality, as it's a complete undirected graph. So all edges are like equivalent for the first weight 2. So we can assign any edge a weight of 2. So maybe I should keep this example aside. Yeah, we should keep this example aside, and maybe we can create a copy of this again. I hope this. So I'm just making this graphs copy again. And now what I'm saying is the first edge of weight 2 can be assigned to any edge without loss of generality. And I hope this is clear to you. So I just take any random edge and assign it a weight of 2. And now what we have to do is we have to be a bit careful about placement of these other edges now. So note that so after this 2, so what we actually want to do is, so let's say we run the Kruskal's algorithm first for selecting the MSG. So note that the first edge of weight 2 will always be selected by Kruskal's algorithm because initially each vertex was in different component. And as soon as we pick this edge, this is the least cost edge of, and this connects different components. So this weight 2 edge will always be picked up by Kruskal's algorithm. So MSG will definitely contain this edge of weight 2. And after this 1 and 2 become a single component, right? This 3 becomes one component, this 4 is one component, and these 1 and 2 together become a single component after picking this edge of weight 2. And after this, what happens is, so the next edge to be scanned is an edge of weight 4. So this edge of weight 4 can be any of these remaining 5 edges. But note that any of these 5 edges will also be intercomponent edges, right? Like all these edges are also between components, not in the same component. So again, the edge of weight 4 will also always be picked. So these 2 and 4, these edges of weight 2 and weight 4 will always get picked in our MSG. And we only had to pick 3 edges. So the third edge has a choice of being picked between 5, 6, 8, and 10. But now we'll try to rule out the possibilities for the third edge also. And note that in third edge, we'll try to uh, maximize the weight of the edge. Ideally, we would want something like this edge of weight 10 being selected as the third edge. But we'll see actually that some weights can be ruled out here also. So out of these 5, 6, 8, and 10, we want to maximize the edge. We want to assign these weights such that the maximum possible weight out of these 4 edges is selected. But let's see what we can do out of this. So this 2 and 4 are selected. Let's say initially these 2 and 4 weights get selected. And now what we would want is we would want to rule out 5, right? We would want to say that after adding these 2 and 4, this 5 should actually become an intra-cluster edge so that this does not get added to our MSG. Otherwise, we will be like sort of done and we'll obtain a MSG of size 2 plus 4 plus 5. But we want to obtain a bigger size MSG, right? So for this, what we would want is we would want this 5 to become an intra-cluster edge and not remain inter-cluster. So that we can look at higher weights. Now Kruskal's algorithm can look at higher weights. So this 5 should be, we should try to make this 5 as an intra-cluster edge. So we should assign weights such that this 5 becomes an intra-cluster edge now. So how do we do this? So note that we initially assigned this a weight of 2. And now if we assign this edge as a weight of 4, this 3, 4 edge as a weight of 4, then note that we can never assign the edge of weight 5 as an intra-cluster edge because these 1 and 2 and 3 and 4 will be forming single clusters and all the remaining edges will be intercluster. So what this will result is the edge of weight 5 being also picked. And we sort of don't want that. So instead what we can do is let's make any of these edges. Any of these edges, let's say this edge 1, 4, 1, 3 as the weight 4 edge. So what this results in is initially this 1, 2 edge makes a single cluster. Then this 1, 3 edge also gets picked. And now the cluster becomes this 1, 2, and 3 cluster. Right? And as soon as this cluster becomes a single cluster, now we can have this 2, 3 edge as a weight of 5, as weight 5 edge. And what this helps us in is making this 5 edge as an intra-cluster edge again. So this 5 becomes intra-cluster, and so this does not get picked by Kruskal's. So, but note that that's where some technicality comes in. So this 5 gets rejected. And after this, these are the remaining 3 edges, right? And note that all of these remaining three edges after this 5 gets rejected, all of these three are intercluster edges. Because 1, 2, and 3 form a single cluster, and 4 is in the other cluster, and all these edges are originating from 4. So all these three edges are intercluster edges. So whatever assignment we do for these edges, let's say we assign this as 6, we assign this as 8, this as 10, or any other assignment, uh, what's going to happen is the minimum of these three edges will be getting picked, because all these three edges are intercluster. And the minimum will always be like out of 6, 8, and 10, the minimum will always be 6. So the edges which will be getting picked in the maximum MSG will be the edges 2, 4, and 6. So this we can't do better than this. So the MSG will have a size of something like 2 plus 4 plus 6. I hope this is clear to you, Rasika. If it is not, I can try to repeat the arguments. Otherwise, I'll just write down that the answer is actually 12. And how do we do this? Without loss of generality. So consider the figure below. Consider the given or the figure which we have drawn. And without loss of generality, I'll just write down the arguments which I'm saying right now. Let's assume edge 1, 2 has weight 2. Now, suppose we use Kruskal's algorithm to find the MSG. Then the 1, 2 edge always gets picked in MSG. And what this results in is actually 1 and 2 becoming a single component. And we also know that and what happens is after this, we'll be looking at the edge of weight 4, right? And this will also be an intercluster edge. After this, uh, the edge of weight 4, wherever it is, will also be an intercluster edge, and so gets picked by Kruskal's algorithm. So note that one thing which Rasika initially said, which I forgot to mention, was uh, note that the MSG contains three edges. So we'll be looking to find the MSG of three edges with maximum weight, right? So now the figure which I had already drawn, in this figure, the edge 1, 2 should have a weight of 2. And after this, the edge of weight 4, wherever it is, will also be an intercluster edge. And so it will also get picked by Kruskal's algorithm. So we only need to pick one more edge. We only need to pick one more edge, and this edge should have maximum possible weight. And this edge should have maximum possible weight. And now what happens is actually when we scan the edge of weight 5, if we make 5 an intracluster edge, if we make it an intracluster edge, it gets rejected And so we can obtain MSG with higher weights. So this is something which we want to do, that we want to make this edge of weight 5 as an intracluster edge. And this can be done by assigning the edge 1, 3 a weight of 4, a weight of 4, and the edge like let's say 2, 3 a weight of 5, and edge 2, 3 a weight of 5, or maybe the weight 5. The weight 4 and 2, 3 the weight 5. But note that as soon as we do this, after rejecting 5, the 1, 2, and 3 form a single component. So note that after rejecting edge 5, the edges 1, 2, the vertices 1, 2, 3 are part of the same component. And so all the remaining edges will be intercluster. So that's what I was saying, that these 1, 2, 3 become single component, these 1, 2, 3, and now the remaining 3 edges will be intercluster. And so since the weight 6, 8, and 10 have to be assigned to those, so we'll first be scanning the edge 6, which will be intercluster, and so we'll be picking the edge 6. So in any assignment, for the remaining edges, the edge of weight 6 will always be picked. And what this means is that, so maximum possible weight of MSP is equals to 2 plus 4 weight edge plus the 6 weight edge, which is actually equal to 12. So 2 plus 4 plus 6 is 12. And this is our answer. So I'll just underline this. So I'll post the figure here while uploading the document. But yeah, this is the main crux of the argument. Okay, so Siga is saying that she got it. So nice. So yeah, if something is still unclear, you can tell me and I'll try to explain it again. Otherwise, I guess we can move on to the next question. Okay, so next question is again compute the cost of MSG in the given figure. So it's a boring question again, and I believe we have discussed this, a lot of variants of this, so I'll be skipping this question. So yeah. So maybe we can do something else. So let's move on to the sixth question now. So the sixth question says, let G is equal to V comma E be an undirected connected graph having distinct positive weight edges. So the graph G has edges with different positive weights. So no two edges have the same weight. And now let V be partitioned into two non-empty subsets X and Y. So what we are saying is we are partitioning the vertex at V into two subsets X and Y, and let S be the set of all edges where one end of each edge belongs to X and another belongs to Y. And now we are saying consider single edge E which has strictly lowest weight among all edges in set S. Which of the following would be true? So I would like to give a diagrammatical depiction of this problem. So what we are actually saying is, so that suppose we are given this set X of vertices and we are given the set Y of vertices. So note that X union Y is the set of all vertices in the graph. So now note that there may be some edges. So there will be some edges going from here to here. Like, and there can be multiple edges going between these two. Yeah, I'm not able. Yeah, something like this. So there can be multiple. So there can be multiple endpoints, right? So there can be one vertex v1 here, one vertex v2 here, one vertex v3, v4. So there can be multiple edges going between the sets x and y, going across these sets x and y. And now we are saying that consider an edge E. So let's call this edge E. So the property of this edge E is that it has the lowest weight among all these edges. So let's say, or maybe we should call this edge E. Let's say this edge is something like E1, this is E2, E3. And now what we are saying is that E has strictly less weight than all of these E1, E2, E3. Like all edges have distinct weights that was given to us initially. So E1, E2, E3 have distinct weights. And this edge E has the strictly lowest weight among all edges of the set S. So this is the set S of edges which we are talking about, the set E, E1, E2, E3. And it can go on till some En. Like there can be multiple edges. And now when we look at this set, this edge E, we need to say which of the following is true. That edge E would be present in all the MSGs of the graph. Edge E would not be present in any MSG. Edge E would not be present in all, but would be present in some. So which of the following statements is correct? So any ideas, Rasika? What should be the correct answer here? So note that edge E is the smallest weight edge. So E has a lower weight than E1, E2, and E3. So okay, so Rasika is saying that edge E would not be present in all MSGs, but would be present in some of the MSGs. So actually, Rasika, this would be not correct. Actually, the correct answer should be this, that edge E would be present in all MSGs. And why is this the case? So we can just see it ourselves here only. So let's suppose there was an MST in which the edge E was not present. Let's say the edge E1 was present in that MST instead. So E is not present, but E1 is present, let's say. Now what I can do in that MSG is I can perform an operation that I can remove E1, and instead of that, I can add E to that MSG. Let's say E1 had a cost of 5, E had a cost of 4. And the MSG which I obtained, which did not contain E, but contained E1, had a cost of, let's say, 10. Now what happens when I remove E1 is that the 10 cost removes, the cost reduces by 5, and now I add the edge E, and so the cost increases by 4. So the final cost of MSG will come out to be something like 10 minus 5 plus 4, which will be something like a 9. And 9 will be strictly less than 10. So actually we will obtain a smaller spanning tree, which will be a contradiction as MST is the spanning tree with the smallest cost. So I did a bit hand wavy argument orally, but did you get the essence of it, Rasika? So what I'm trying to say is just assume that E1 has a weight of, let's say, 10 and E has a weight of 6. And now let's assume by contradiction that there exists a minimum spanning tree which does not contain E. So it must contain at least one of these edges, right? One of these E, E1, E2, E3, because X and Y component need to be connected with each other. So let's say it contains E1 and E1 had, let's say, a weight of 10 and this E had a weight of, let's say, 5. So instead of selecting E1, if I would have selected a 5 in my MSG, I would have obtained an MSG of lower weight. So does this make sense? Okay, you got it. Nice. So actually the answer should be that it is present in all MSGs. And I will type down the also. So the answer is option A is correct. And why is this? Maybe I should first implement the correct answer. This is because suppose there exists an MST T. So let's call this MST T in which does not contain E, which does not contain the edge E. Since the MST has to connect the sets X and Y, so the MST should connect these two sets X and Y, right? So one of the edges going across this MST should be present inside. So one of the edges going across X and Y, one of the edges of the set S of set S. So set S was defined as the set of edges. It was defined in the problem only. So one of the edges of set S should be present in the MSG. Let's say that edge is E1. So let's say the edge is E1. And we know that E1 is not equal to E. E1 is not equal to E. And why is this the case? Because we have already assumed that MSGT does not contain the edge E, whereas MSG contains the edge E1. So what this means is that maybe now consider the spanning tree. So also what we know is like E1 is not equal to E. So what we know is so weight of E1 is strictly greater than weight of E. And why is this the case? This was given to us that E is the strictly lowest weight among all edges. Right? Since this was given that E has a strictly lowest weight, so what this means is that weight of E1 will be greater than weight of E. So what we do is we consider the spanning tree T prime, which is just the spanning tree T, and we delete the edge E1 from this and instead add the edge E into it. So note that this will still form a spanning tree. First convince yourself that this will also be a spanning tree. Like deleting an edge which goes between these two components and then adding an edge between these two components, adding another edge will still result in a spanning tree. And I hope this is not too difficult to see by yourself. So if we are able to do this, then it is easy to see that weight of T prime is less than weight of the original MSGT, which is a contradiction as MST should have the lowest weight, right? So what this means is that so edge E is present in all MSTs of G. So I hope this is clear to everyone. Otherwise, you can ask me via chat, Rasika. Okay, so this is the correct answer. So option A is correct. So then maybe we can move on to the last question for today. So the seventh question says that if all the edges of the graph have distinct weights, then the minimum spanning tree is unique. Is this true or is this statement false? So true. So Rasika is saying that this statement is true. So actually, yeah, Rasika, so you're correct that this statement is true. And it's not too difficult to see by yourself, like why will this statement be true? So uh, so just consider, so this is sort of easy to see that just consider, so it somewhat the arguments will be similar to the arguments used here. So the argument will be something like, suppose there exist two minimum spanning trees. So, so to prove this, we can use contradiction. Okay. Hmm. Suppose there exist two minimum spanning trees, T and T prime, where T is not equal to T prime. So we want to show that minimum spanning trees are unique. So actually we want to show is something like there cannot exist two spanning trees where T is not equal to T prime. So this is what we want to show. Right. So now I would try to leave it to you guys to figure it out. Like how can we prove that? Suppose there exists two minimum spanning trees T and T prime. So T and T prime will have equal weights, right? So maybe you guys can try it out yourself because it's not too difficult of an argument. So just try to see if these two edges are not, if these two trees are not equal to each other, this means that there will be some edges which will be present in T, which are not present in T prime. But what this will actually mean is that since all edges have distinct weights, we could have actually used those edges to lower the weight of T prime. So, so I will leave it as an exercise. Maybe proof. I will leave it as a try it yourself. And the hint is something like this, that to prove this, yeah, where T is equal to. And now try to show that we can obtain an MST, a spanning tree of lower weight if this is the case. So now we'll try to, so if we have two spanning trees, two minimum spanning trees T and T prime, then try to show that we can obtain a spanning tree of lower weight than these weights of T and T prime. And this will be a contradiction. And note that this property will be used, that all edges have distinct weights. Because if all edges don't have distinct weights, then actually there can be multiple spanning trees, as we had seen in the first question, in this question itself, that there were multiple spanning trees possible, but there were edges which had same weights. If all edges have distinct weights, actually, this is true. So maybe you can try it yourself. So this is the main idea, and the arguments will be somewhat similar to the arguments which I used in the earlier proof. So yeah. Okay, so I guess uh, this is it. These were the questions which I planned on discussing for today. So since there are no questions left now, so I'll just, so while uploading this document, I'll just put these diagrams also into this document. So besides that, so this is done from my side. So if there are any doubts or any comments from your side, Rasika, you can let me know via chat. Otherwise, we can, I guess, conclude the session. If there are any doubts, any comments, any queries, you can let me know. Otherwise, I'll just assume that there are no doubts and we can close the session. Okay, so Rasika is saying that he has no doubts. So I guess that concludes the session for today then. So once again, thanks for joining the session. Thanks for attending this, and hopefully we'll meet next week again, same timing, 6 to 8 p.m. So yeah, see you then. So till then, I guess bye bye, and again, thanks for joining the session. I'll just be closing it now. So bye bye.